So here in this section, we are going to work on few problems based on geometric progression. There will be 5 problems. So let's begin with our first one. Problem number 1. We have a finite geometric progression. It's given here that the term equidistant from the beginning and the end are always the same, and it's equal to the product of the first and the last term. There's a similar statement that we worked with arithmetic progression as well. It stated that if we consider the term equidistance from the beginning and the end of an arithmetic progression, and if we take the sum, the sum is always equals to the sum of the first term and the last term. Here in the case of a geometric progression, it's going to be the product of the first and the last term. So let's begin. So we will consider the first term to be, let the first term be represented by the letter a in lowercase and the common ratio be r. Now we will consider, let's say, the kth term from the beginning of the geometric progression. This will be equals to the first term times the common ratio raised to the power, since it's the kth term, it is going to be raised to the power of k minus 1. So let this be equation number 1. Then we're going to consider the kth term. So this is the term which is equidistant from the beginning as well as the end. This is the kth term. So the kth term from the end of the geometric progression, that's going to be equals to, so we will use the idea that if a is the first term, ar be the second term, ar squared is the third term, then our second last term will be ar raised to the power of n minus 2, and the last term will be ar raised to the power of n minus 1. So we will reverse this given geometric progression, and this is going to give us a times r raised to the power of n minus 1 followed by ar raised to the power of n minus 2. So this becomes the second term, and finally at the end we have ar and a. So in this case, the common ratio, it's not going to be r, but it's going to be 1 over r. So we can check that out. So if we consider the second term, which is ar raised to the power of n minus 2 and divided by ar raised to the power of n minus 1, then this ratio is equivalent to 1 over r. So that means the kth term from the end will be, we will have to consider the first term. So that's ar raised to the power of n minus 1 times the common ratio. So the common ratio is 1 over r whole raised to the power of, since it's the kth term, so we have k minus 1. Now ar raised to the power of n minus 1, this is also the nth term. So we have an times 1 over r raised to the power of k minus 1. So let this be equation number 2. Now we have to show that the product of these two terms, so we'll take ar raised to the power of k minus 1. So this is the kth term from the beginning. If we multiply it to the kth term from the end, which is an times 1 over r raised to the power of k minus 1, then this is going to be equals to, so we have a multiplied to an, the nth term, and we have r raised to the power of k minus 1 multiplied to 1 over r whole raised to the power of k minus 1. So these two terms will cancel out. I mean, they will factor out to give us 1, and this leaves us with a value a times an. That means simply the product of the first term and the last term. Let's move on to the second problem. Problem number 2. So we have to determine all the sequences that are both a arithmetic progression as well as a geometric progression. So let's begin. We will begin by considering a sequence. Let's call it an. This is a sequence that is both an arithmetic sequence and as well as a geometric sequence. Now we will consider the last we'll consider 3 terms here. Let the terms be the nth term, the term next to it will be an plus 1, and the next term, which is an plus 2. Then these 3 numbers are in, we'll consider the first, they are in arithmetic progression. Since they are in AP, which implies that 2 times the middle term must be equals to the first term plus the third term. So let this be equation number 1. Also, these 3 same numbers, an plus 1 and an plus 2, are in geometric progression with a common ratio r. So we're defining the common ratio as r, and first term as a in lowercase. Then it follows that the nth term an will be a times r raised to the power of n minus 1. the n plus 1th term will be a times r raised to the power of n, and the n plus 2th term, that will be a r raised to the power of n plus 1. So we'll substitute this value back into equation number 1. So we have 2 times a r raised to the power of n. This is equals to the nth term a r raised to the power of n minus 1 plus the n plus 2th term. So that's a times r raised to the power of n plus 1. So we can have 2 times a r raised to the power of n equals to a times r raised to the power of n times r raised to the power of negative 1 plus a times r raised to the power of n times r. What we can do here is we can take a as the common factor as well as r raised to the power of n. So this is going to leave us with 2 equals to, so here we are taking a times r raised to the power of n as the common factor. So r raised to the power of negative 1 plus r. So here we have 2 equals to r raised to the power of negative 1 plus r, and this is simply r plus 1 over r, which is r squared, but we're going to multiply throughout by r squared, and rearranging the equation we're going to get r squared minus 2r plus 1 equals to 0. So this is simply r minus 1 squared equals to 0, which means our common ratio is 1. So we'll obtain the condition that when these three numbers are in arithmetic progression as well as in geometric progression, then the common ratio is going to be equals to r. So that means these three terms can now become an will be equals to an plus 1th term, that's equals to an plus 2th term, that's equals to a. So in a sense, the common ratio being 1, we can say that the sequence a, so a1, a2, a3, these are the terms up to the nth term. So a1 corresponds to a, a2 corresponds to a, a3 corresponds to a. These are all the sequences having a term value equals to a. So these are in both arithmetic progression as well as in geometric progression. So let's move on to the next problem. Problem number 3. It's given here that the products of the corresponding terms of the two sequences where both of them are in GP also forms a geometric progression. So let's say, so here we have AR squared, all goes up to the nth term. This has a common ratio of r since it is in GP. Then we have AR squared going all the way up to the nth term. We have AR raised to the power of n minus 1 has a common ratio of r in uppercase. Now what we're going to do, we're going to multiply the corresponding terms. We have a times a equals to a times r equals to a times r squared. Going up to the nth term, we have a r raised to the power of n minus 1 times r raised to the power of n minus 1. So we have to show that this is also in GP. So first let's calculate the common ratio r. We're calling it r1. So this is going to be the second term AARR divided by the first term, which is AA. So we're getting a common ratio r times r. Then we have the third term r squared divided by AARR. This is also going to give us r in lowercase multiplied with r in uppercase. So here the product of the common ratio of the first AP and the second AP, so that meaning the resulting AP, this is also in a geometric progression. Let's move on to the next problem. Problem number 4. We have a certain culture. Here the number of bacteria is doubling each hour. Also there are 30 bacteria present in the beginning. We need to find out the bacteria that will be present at the end of the second, fourth and the nth hour. Now clearly this means that the number of bacteria at the end of different hours is going to form a GP with a first term of 30, because this is the initial amount of bacteria that's first present at the culture, and since this is doubling, it is going to have a common ratio of r equals to 2. Now we have to find out the amount of bacteria present at the end of the second hour. So actually the end of the second hour, this is the third term of the GP. This is the third term of the GP, which is actually a times r raised to the power of 3 minus 1. So here a value is 30, r value is 2, so we're 2 raised to the power of 2. So 2 squared is 4, 4 times 30 is 12. We can also verify, since the amount of bacteria started with 30. So this was originally it started out with 30 amounts of bacteria. Then after 1 hour, it doubled to 60. So this is the first hour, or you can say the end of the first hour. Then again after the end of the second hour, so this became 120. So this is the after the end of the second hour, and we can see that this is actually the third term of the geometric progression. Then we can also obtain the amount of bacteria present at the end of the fourth hour. So at the end of the fourth hour, so this is the end of the second hour, end of the fourth hour, this will be equals to the fifth term. So it will be simply the fifth term of the geometric progression, which will be equals to 30 times 2 raised to the power of 5 minus 1, which will be equals to 480. Now we can find out the amount of bacteria at the end of the nth hour. At the end of the nth hour, so this is going to be the n plus 1th term of the geometric progression, which will be equals to the first term being a times the common ratio, which is 2 raised to the power of n plus 1 minus 1. That means we have 30 times 2 raised to the power of n. Let's move on to the next problem. So here we have a manufacturer who is estimating that the value of a certain machine that currently costs 15,625 per unit will be depreciating at the rate of 20% per year. What will be the rate of the depreciated value after 5 years? So let's say that the initial value, let it be represented by V0. So this is 15,625 per unit. Then we have the rate of depreciation. So it's given here that the rate of depreciation is 20%. Now, what will be the depreciated value after the end of first year? So let's say after the end of the first year, so it started out with V0, then it is going to get depreciated. So we'll have to subtract 20% of V0 from it, which will be V0 minus. So 20% is 1/5 of V0, or simply V0 multiplied to 1 minus 1 over 5. So let's represent it by V1. Then after the end of second year, it's again going to get depreciated with the same value of 20%. So we're V1 minus 20% of V0, which will be equal V1 of the initial value. So we have V1 minus 1/5 of V1, which will be equals to V1 times 1 minus 1 over 5. Now we've already obtained the value of V1. So V1 will be equals to V0 times 1 minus 1 over 5. Multiply to 1 minus 1 over 5. So this will be whole squared, and we can call it V2. So here we can find out at the end of the nth year. So here we can say that this will be equals to V0 times 1 minus 1 over 5 raised to the power of n. Now in our question, we are to obtain the depreciated value after the end of 5 years. So that means when n equals to 5, this implies that our depreciated value, so the depreciated value will be equals to V0 times 1 minus 1 over 5 raised to the power of 5, which will be equals to V0 times 4/5 of raised to the power of 5. So V0, that has a value 15,625 multiplied to 4 divided 5 raised to the power of 5, and this is going to give us a value 5,120. So that means the value which started out with 15,625, if it depreciates by a rate of 20% per year, at the end of the 5th year, its depreciated value will be 5,120 per unit.